Hello and welcome back. Welcome back to science. Today we're going to be talking about chapter 2, section 4. We're going to be talking about chemical reactions. So this is really the heart of the chapter in my opinion. We're going to focus on enzymes and we're going to look at different kinds of reactions. So a chemical reaction they're going to use up reactants and they're going to rearrange them and to make new products. So an example is A plus B, they exist, but in the end, they may be put together. Or you could take something more elaborate like AB plus CD is going to produce AD plus CB. And so this rearrangement is just showing that those chemicals are not recreated, they're not um, formed, they're rearranged. And that's what happens in a chemical reaction. So here we have a chemical reaction. We show that water is being broken or is being formed. So the thing that is being broken, that's being rearranged, that's the chemical bonds. So the bonds that are going to be holding together this hydrogen or the bonds that are holding together this oxygen, they're all going to be broken and rearranged to form that structure that we're looking at. And so we are rearranging this, and we're doing this by breaking and forming bonds. So let's go ahead and look at some of the different parts of a typical chemical equation. And so we're going to do that by looking at the products, the reactants, the coefficients, and subscripts. So before you look at the actual chemical equation, the before number, this is the coefficient, just like in math, nothing new here. But we have the coefficient, that's the number before, and you can see the subscripts are written to the right below each atom. And we can look at the actual atoms that are there. Then we can look at the reactants are the things that are going to be rearranged. The products are going to be the things that are produced from this reaction. Also, you need to notice that this arrow is pointing at the products. Think of a little child that's looking at this, that's actually proud of their work, of what they made, and so they're pointing at it. So you point at the products. I want you to do the same here on this chemical equation. That's CO2 plus 6H2O. In the presence of something is going to yield C6H12O6 plus O2. And so we know that this is going to be the equation for photosynthesis, one I definitely want you to know. So notice that underneath it there are spaces. I want you to write the names of those things: carbon dioxide, the water, the carbohydrate being glucose, and oxygen. But I also want you to go a step farther, and I want you to identify the things like product reactants, coefficient, and subscript. So make sure that you do this. And so I'd write that word, and then I would identify what each thing is. So one word to identify many of the different things. Okay? So take a moment, see if you can figure out how to do that with our notes. You can use Cami, or you can use DocuHub to write on PDFs. Or you can use some of the insert diagrams or figures on Google Docs. So multiple ways to do this. All right, now that you have done that, you either pause me and do that, but now let's go ahead and move on. So if we have CO2 and water and the presence of light, we're going to make a carbohydrate and oxygen. This is the equation for photosynthesis. Notice that we have the reactants and the products, and we're pointing at the products. Now, when we look at endothermic and exothermic reactions, these are two kinds of reactions. So we can see our reactants here, we can see our products there, going from reactant to product. An endothermic reaction is going to absorb energy. It's going to take energy from that environment. So this is the direction of the reaction, kind of the course of the reaction, and we're going to see that we go from reactants to products. On your notes, it's asking you to identify where the reactants are and where the products are. Also, it's going to ask you to go back and identify the activation energy. We'll talk about that one in just a minute. So here's an example of an exothermic reaction. So exothermic reaction, you're going to have the reactants, you're going to have the products, and we're going to go, this is going to release heat. So this is going to release heat into the environment. You can find a great example with hot hands, these hand warmers where you break open and you expose them to air and you twist them a little bit, and then they get hot and they stay hot for a while. So this is an exothermic reaction. It's a reaction that releases heat into the environment. So when we're looking at proteins, specifically enzymes, they can be denatured. They can be changed by two things, and that is temperature and pH. Now, temperature, you may find that in the cooler temperatures, they don't really work well. But in the warmer temperatures, they stop functioning altogether because they're denatured. So this, they can't really work at maximum rate, but this is where they just can't do their job at all. And so this is the fall off where we have it denatured. Denature is to misshape. Imagine a key that you would have to work a door, and you hit that key with a hammer. It may look like parts of the key, like normal, but the odds that you could fit it in and actually work it, not very likely at all. So that lock and key kind of analogy works there. Another is temperature. So we have the optimal temperature and optimal pH. So things are the proteins, specifically we're talking about enzymes. They are denatured. They're changed their shape due to a temperature or a pH. Imagine you have a Lego block and you put the Lego block into the oven, just enough to get it kind of gooey a little bit. So those pegs may not line up perfectly. They may have shifted a little bit. So it looks a lot like the Lego did, but it's not functional. It can't be used with the same integrity or the same functionality as the typical Lego block. And so those pegs, those posts are no longer functional. And so that's going to be a non-functional because it was denatured through heat. Or you can think of pouring some hydrochloric acid on something like that, causing the shape to change or erode away. And that would be kind of a model of denaturing through pH. So number 6, we're looking at activation energy. This is the energy needed to get the reaction going. And so we have the reactants, we have the products, but we have to input this much energy to make the reaction happen. If we don't put that energy in, we don't have that chemical reaction. So this is the energy of activation, also called activation energy. So to go from reactants to products, you have to have the activation energy needs met, and then it's just an easy downhill process. So you need the activation energy to start a chemical reaction. Now, when we look at proteins, now proteins can be, because all enzymes are proteins, they can be misshapen. You can see the structure, you can see random proteins, you can see this alpha helices, the beta pleated sheets that's there, all this really cool parts of the enzyme. But all enzymes are made of protein, but not all proteins are made of enzymes. So let me just make sure you get it. Proteins include things like collagen in your skin, fingernails, spider webs, antibodies, but it also includes enzymes. All of those are proteins, but one of those categories would be the enzyme. So this just to show you that all enzymes are protein, but not all proteins are enzymes. All right, our final step is to look at this activation energy. So the energy that you need to go from reactants to products. So this is the activation energy. Notice that without an enzyme, there's a lot of energy needed. With an enzyme, it's going to make this a much easier process. So enzymes, here's what they do. Enzymes lower activation energy. So make sure that you get that. So enzymes lower activation energy, which allow you to get from a reactant to product faster and with less energy input needed. All right, guys, this is an overview of 2.4. Make sure you're reading through and getting ready for the test. Bye-bye.